Another classic condensation reaction between carbonyls is called the Claisen condensation. This is when two esters react with each other. We'll start with an example of a self-condensation example involving ethyl acetate. If we add base, such as sodium methoxide, one molecule will form an enolate, so let's say it's this one, that would attack the other ester, eliminating the ethoxy group and forming this beta ketoester. This is the typical Claisen product. You might recall that aldo reactions typically will give you initially a beta hydroxycarbonyl, and then that dehydrates to form an alpha beta unsaturated carbonyl. In the case of the Claisen reaction, we typically get a beta ketoester. We also usually get a small molecule like ethanol or some other alcohol that is the leaving group on the ester. Notice that the base that we typically use is usually the conjugate base of the leaving group that we're going to be using for the ester. So we have ethoxy groups on the acetate molecule. So that is the base that we will use for this reaction. Let's take a look now at the mechanism for the Claisen reaction. So the reaction starts with a base, such as ethoxide, deprotonating an alpha hydrogen on one of the ester molecules. That forms an enolate, as shown here, which will attack the carbonyl of another ester molecule, forming a tetrahedral intermediate, as shown in the next structure. This tetrahedral intermediate will reform the carbonyl by eliminating the ethoxy group, the leaving group on that ester. After eliminating the leaving group, we end up with a beta ketoester, which is the typical product of the Claisen reaction. But in reality, under the basic conditions that we use for forming this Claisen reaction, notice that generally one of the alpha hydrogens on this beta ketoester is usually deprotonated by base, ethoxide for example, to form an enolate, and it is later when we convert this enolate back to the beta ketoester by adding acid. So in the Claisen reaction, we usually include a second step where we have to add acid to get rid of not only the base, but also turn the enolate of the beta ketoester product back to a beta ketoester. In this question, we're going to determine the product from the Claisen condensation of this ester shown here. So we have an ethyl leaving group on the ester, and then besides the carbonyl carbon, we have 1, 2 carbons more, a third one from one of the methyl groups, and of course a methyl substituent. So if we do a self-condensation reaction of this ester shown here in the reaction, and we add base, an alpha hydrogen from the ester will be removed and form an enolate, which then attacks a second molecule of the same ester, eliminating the ethoxy group. That should lead us to a beta ketoester. So the left side of the structure here is from one molecule, that's the electrophile or the Claisen acceptor. And the right side is the molecule that forms the enolate. So that would be this one here. That is our Claisen donor, or the molecule that forms the enolate. Similar to the cross or the mix aldo reaction, the mix or cross Claisen reaction can potentially give you 4 possible products. We can use strategies to eliminate some of these products and hopefully obtain a single product. One of those strategies is to use an ester that doesn't have alpha hydrogens and therefore can form an enolate. And as a result, it will be the acceptor in the reaction or the electrophile in the reaction. Here's an example where that strategy is used. So mixing ethyl acetate and ethyl benzoate plus base should lead to a Claisen reaction where a single product is obtained. So ethyl acetate has alpha hydrogens. So sodium hydride, which is a base, will remove one of those alpha hydrogens, forming an enolate. Then that will attack the ethyl benzoate. The ethyl benzoate, notice, doesn't have any alpha hydrogens, so it's not going to form an enolate. So the enolate of ethyl acetate will attack this electrophile ethyl benzoate and form the following beta ketoester. So in blue is the structure that came, or part of the structure that came from ethyl acetate, and the bond to the carbonyl of what used to be the ester in ethyl benzoate is drawn here. We also eliminate the ethoxy group, which becomes an ethanol molecule as a byproduct. Note that using an excess of ethyl benzoate or adding ethyl acetate slowly to the reaction will ensure that the enolate of ethyl acetate, once it's formed, will only see or mostly see other molecules of ethyl benzoate rather than other molecules of ethyl acetate to react with. So in other words, by either adding an excess of ethyl benzoate or adding ethyl acetate slowly, we will ensure that the enolate of ethyl acetate will only react with ethyl benzoate rather than with another molecule of ethyl acetate that hasn't formed an enolate yet. Here's an example of a Claisen-like reaction involving a ketone and a ester. The ketone has alpha hydrogens, so when we add base, one of those alpha hydrogens will be removed to form an enolate. That enolate will then react with ethyl formate. Note that ethyl formate does not have alpha hydrogens, and so it can't form an enolate. So once the enolate of the ketone attacks the ester, it eliminates the leaving group, and you'll end up with this beta keto aldehyde. A second strategy that we can use to ensure that the Claisen reaction goes smoothly is to preform an enolate from one of the esters. That would ensure that one partner is the only one that forms the enolate, and then add in a second ester to act as electrophile. So in this example, we're using an ester, we're adding LDA to form an enolate on the alpha carbon, and then that enolate will attack the ester we add in the second step, eliminate the leaving group, and form a beta keto ester. You can see highlighted now on the left side of the structure, this is the structure that is added from the ester, this one here, that forms the enolate. And then the ketone and the remaining carbons, so that would be these carbons here, will come from the electrophile of this reaction. In the last example on this slide, we have again an ester, and we're going to add LDA to form an enolate at this alpha carbon. That would react with another ester molecule, forming a beta ketoester. In this question, we want to predict the product that you would expect from a mixed Claisen reaction between the two esters that are shown in this structure, in this example. Comparing the two esters that we have here, notice that diethyl oxalate does not have alpha hydrogens, so it's going to be our Claisen acceptor, while ethyl acetate has alpha hydrogens, which are acidic, so if we add base to it, we'll form an enolate on this alpha carbon. That alpha carbon will then react with one of the two ester functional groups on diethyl oxalate. That will lead us to forming a beta keto ester. So again, the structure or the part of the structure that came from ethyl acetate is shown here, now highlighted. And then on the left side, we have what remains from diethyl oxalate once the enolate nucleophile adds to it and displaces the ethoxy group. The intermolecular Claisen reaction is sometimes referred to as the Dieckmann condensation. Just like the intramolecular aldo reaction, we want to form 5 and 6 member rings. With a 1,6 diester, we typically will form a 5-member ring, as shown in the product. Addition of base to this diester leads to forming an enolate in this carbon, which attacks the other ester, forming a cyclic ketone, which has a beta ester, which is external to the ring. In the next example, we have a 1,7 diester, which typically gives you a 6-member ketone with an external ester. In this example, base will deprotonate this carbon, or the hydrogen on that carbon, which then attacks the other carbonyl of the other ester, forming a cyclic ketone with this external ester. Note that this reaction works best when we are working with a symmetrical 1,6 diester or a 1,7 diester. If we have an unsymmetrical diester, then we'll have the possibility of forming 2 or more products. Here's an example of the mechanism for the intramolecular Claisen reaction or the Dieckmann reaction. So base will deprotonate the alpha hydrogens on one of the 2 esters. That enolate that forms will attack the other carbonyl, breaking the double bond, forming this tetrahedral intermediate. It then reforms the carbonyl by eliminating the leaving group. The resultant product, which is a beta ketoester, just like in the normal Claisen reaction, is very acidic. So under the basic reactions of the Dieckmann condensation, the base will remove an alpha hydrogen, which is in the center of 2 carbonyls, forming an enolate. And then once we add aqueous acid at the end of the reaction, we can go back to the beta ketoester. Claisen-like condensation reaction occurs in the biosynthesis of cholesterol as well as fatty acids. Generally, the reaction involves transfer of an acetyl group from acetyl coenzyme A onto the thiol group of the enzyme that is involved in this reaction. That leads to this thioester, which will react with the enolate of another thioester of acetyl coenzyme A. So in this step, the alpha hydrogen of this thioester will be removed by base, forming an enolate, which will then attack this other thioester and do a Claisen-like reaction, forming this tetrahedral intermediate, which then reforms the carbonyl by eliminating the leaving group and giving us a beta keto thioester. For example, we have a 1,7 diester that will be treated with base in an intermolecular Claisen or a Dieckmann reaction. The ester that is in this question is a symmetrical 1,7 diester. When treated with base, it will form an enolate out of one of the 2 esters, and it doesn't matter which one you use since we're dealing with a symmetrical molecule. This carbon will then attack the carbonyl of the ester, eliminate the leaving group, and it should form a 6-member ring. You can sort of map this reaction out by counting or labeling carbons. So that is carbon 1, this is 2, this is 3, this is 4, we have 5 here, and then we have the carbonyl carbon, which is number 6. So in our product, this would be carbon 1, this would be 2, 3 has a methyl group, just like in the reactant, 4, 5, and then the ketone carbon is 6. Remember, that is the carbon that used to be an ester and we eliminated the leaving group. We also have this external ester, which is this one here.